are moving into chapter 6 now. The first thing we're talking about is area. Now we have done some areas before. We did like the area between a curve and the x-axis, right? And when we did those, we used the techniques of like breaking it into rectangles, and remember that we had to specify the number of rectangles and add up the areas length times width, and we had left-hand sums and right-hand sums and midpoint sums, and eventually we talked about to get the best approximation, what has to happen to the number of rectangles? It has to go to infinity, right? And so by the end of that section, we were doing the limit as the number of rectangles went to infinity of that sum. So this section, we're going to do something a little bit different. We're not going to find the area between a curve and the x-axis. We are finding the area between two separate curves, two separate functions. The idea is kind of the same. So we could break these into rectangles and add up all of those, and we know that then to get the actual area, we need the limit as the number of rectangles goes to infinity of the sum from 1 to n. Okay, length times width. So the width of all of these is the change in x. The height, you would have to do what? How would we measure the height of these? I want to know how far it is from here to here. What would you need to do? Well, okay, just more generic than that. So, if we're talking about, so let's say at this particular point, the y value is 3, and at this point, the y is -2. How far apart are those? 5. How do we get it? Or you could do 3 minus -2, the top minus the bottom. So in terms of these functions, if you want to measure the height, you have to do the top function minus the bottom function. Okay, but when we did this, and we had the number of rectangles going to infinity, eventually we said, oh, this is just the same thing as the integral. Remember when we first started out with integrals, we were calculating them by using this summation? So really, if I want to find the area between these two curves, all we have to do is integrate. So we're going to integrate from a to b, that's from a starting x to a stopping x, the top curve minus the bottom curve. What do you think would happen if you did the bottom minus the top? You get a negative. And if we're talking about the area between them, would it be possible to be negative? No. So we can't just put them in any order. We need to make sure we figure out which one is larger and put that one first. Okay, let's look at some problems. I want the area of the region bounded above by y equals e to the x, below by y equals x, and bounded on the sides by x equals 0 and x equals 1. Let's draw a picture, see if we understand what's going on here. So I'm going to start out with an xy. Okay. First thing I need to graph y equals e to the x. We are starting at x equals 0 and ending at x equals 1. So x equals 0 is here, x equals 1 is here. So we're just going between those two x's. Or you could think of those as like vertical lines. Okay, it's going to tell me where to start and stop. Y equals e to the x. What's e to the 0 power? 1. And If I put in a 1, e to the first, that's like a 2.7. So this is curved kind of like that. Okay, then my other one was y equals x. So that's the identity. 0, 0, 1, 1. So we are finding this area right here. How much is contained between those? When we set this up, if we are going to use x's for our variables, everything has to be in terms of x. So my upper and lower limits have to be x values, all my area or all my equations have to have x's, and what would be at the end of this? Dx. Okay. So where is my starting x value? 0. My ending x value. Okay, when I set up my functions, you have to do top minus bottom. So the top one was y equals e to the x. So we're just putting the e to the x minus the bottom one was x. Okay. So now we integrate. What is the antiderivative of e to the x? Minus antiderivative of x. So if we plug in a 1, we get e to the first minus 1/2 times 1, so e minus 1/2. Minus, if you put in a 0, e to the 0 is 1, minus 1/2 times 0 squared is 0. I get e minus 1/2 minus 1, or e minus 3/2. And that is the actual area contained between those two curves. Is that okay? Strongly encourage that picture so you know which one is on the top and you set up your integral correctly. If you work it out and you get a negative, you know you've done something wrong. Either you flipped them originally or you made a mistake in your calculations. So let's look at this one. I want the area of the region enclosed by the parabolas. Y equals x squared and y equals 2x minus x squared. Now this one's a little bit different because did I give you a starting and a stopping point? No. When I say enclosed by these, that means these graphs meet somewhere and I want to integrate between their meeting points. So in order to figure out where they are equal to one another, we're just going to set them equal. They're both equal to y, so they can be equal to one another. Okay, quadratic, so you put everything on one side. What can you do at this point? Set each to 0, so we get x equals 0 and x equals 1. So I might give you x values to go between, or you might have to find their intersection points and use those. So we're going to start at 0. We will end at 1. All right, so let's figure out what these graphs look like. So if I put in a 0, graph this one first. 0 squared is 0. 1 squared is 1. If you want more points, you could put in 1/2. 1/2 squared is 1/4. You know, parabolas curve up. It's just looking something like this. Second one if I put in a 0, 2 times 0 minus 0 is 0. If I put in a 1, 2 times 1 minus 1 is 1. If I put in 1 half, 2 times 1 half minus 1 half squared, I get 1 minus 1 fourth, or 3/4. So we can tell this is a downward facing parabola, so it's kind of curving the other way. It's going to look more like this. My graph's a little bit off. But we are finding the area between them. So this part right here. So when you set this up, we're using x's, so everything has to be an x value. So my starting x is 0, my ending x is, right? My top function is minus my bottom function, which is, and then at the end we put dx, which tells us we're integrating in terms of x. You might want to clean it up a little bit first, just combining like terms. So you just get 2x minus 2x squared dx. Antiderivative of 2x. X squared minus antiderivative of 2x squared. 2/3 x cubed from 0 to 1. So if we put in a 1, minus put in a 0, and we get 1/3. Any questions on that? All right, if I want the area of the region bounded by, and then I gave you 3 different lines. So what do you think we need to do? Graph. Okay, right away I know I've got x equals 2. What's that? Vertical line at 2. So that's probably going to be my stopping point. But did I give you where we're starting? Did I give you the other x value? So what should I do with these two things? Set them equal to each other so I can find out where they meet. So I need x to equal 1 over x squared. Multiply over your x squared, so you get x cubed equals 1. Cube root, so x is 1. So I know when I go to integrate this, I'm going to start at 1 and end at 2. You're going from your small number to your big number. We need to get the rest of the graph. Y equals x. What's that? 0, 0, 1, 1, 2, 2. Y equals 1 over x. I can't do 1 over 0, kind of like an asymptote. 1 over 1 is 1. 1 over 2 squared is 1/4. If you put in 1/2, you get 4. So what it's doing is kind of looks like this. But the important part is knowing where we're starting and stopping and which one is on top. So your graph doesn't have to be perfect. So I'm going to set this up from 1 to 2. F of x is the top function, which is y equals x, so we'll just put in x, minus the other y value was 1 over x squared, or x to the negative 2. They're the same. And then don't forget your dx. Alright. So for antiderivative purposes, it probably is nicer to write that as an x to the negative 2. So antiderivative of x would be minus antiderivative of x to the negative 2. Negative x to the negative 1. From 1 to 2. If you put in a 2, 2 squared is 4 times a half is 2. 2 to the negative 1 is 1/2.
Wouldn't the x be positive? It wouldn't end up being.
Oh yes, thank you. That would be a plus. Minus, put in a 1, we get 1/2 plus 1. So this one is equal to 1. I'm going to keep the first curve the same, but the second equation, I want this to be y equals 1/4 x. Alright. Did I give you any x values at all? No. So I'm not telling you where to start and stop. I'm saying bounded between these curves, so that means they should meet twice, and we want the area between those meeting points. So we have to figure out where they meet to start with. Alright, so to figure out the intersection points, we're going to set those curves equal to one another. What would you do? Right, we can multiply the square root over here. You could even, 1/4 x, isn't that the same thing as x over 4? So could we just cross multiply and get rid of all the fractions at once? So we would have 4x equals x times the square root of x squared plus 1. If I set this equal to 0, I can't actually subtract those things. But what could we do? What did you say? Let's take out an x. I think that would be the easiest option. And then you have two things multiplied that equal 0, so you can set each of those to 0. So we know one of the points is 0, the other one. I would square now. X squared equals 15. Square root plus and minus, so we actually get two values. Okay, this is gonna be pretty, isn't it? So, here's 0. Say this is a positive square root of 15 and a negative square root of 15. Okay, I don't need perfect graphs, I just need to know which one's on top, right? So let's plug in enough points to figure that out. So if I take this one, if you put in 0, you get 0. If you plug in the square root of 15, you get the square root of 15 over the square root of 16, so square root of 15 over 4. Okay, if you plug in a negative square root of 15, you get the same thing except negative. Now, is that enough points to really know what this looks like? No. Could we do more? Sure. If you put in like a 1, you get 1 over the square root of 2. Okay, obviously this isn't a pretty problem. Why don't you give me a decimal approximation for that? What is 1 divided by the square root of 2? Okay, so I'm going to show you, let's hold on just a second, I'll explain why that's important. So if we put in a 1, we get a point 0.7. Okay, not great, but this will kind of get us somewhere. My graph is definitely not to scale at all. If I put in a negative 1, I'll get a negative 0.7. Right, so really, keep in mind, all I'm trying to do is figure out which one of these things is on top, right? So I don't know totally what this looks like yet. I'm going to even just come back to it in a second. What's 1/4 x? We know how to graph that, don't we? It's just a line. So this one would be a lot easier to graph. You put in 0, you get 0. If you put in 15, you get the square root of 15 over 4. But if we put in 1, we get 1/4. Now, my graph is completely not to scale, so this is not even, I'm going to have to drop that down for it to work. So we get that, but the ultimate thing, when you put in 1 for the other one, you got 0.7. So what's bigger, 1/4 or 0.7? The 0.7. So what that's showing me is this other one is on top there. Negative 0.7 is smaller than negative 1/4, so it's on the bottom here. So how many intervals will I have to have? 2. So I'm going to integrate from negative radical 15 to 0. For that section, which one was on top? The 1/4 x minus the other one was x over square root of x squared plus 1. Plus, and I'm going to go from 0 to positive radical 15. And in that section, the other one was on top. I know this one's ugly. Okay, I'm using it to make a point in a few minutes, but have I lost anybody? All right. So if I go to integrate, I can integrate the 1/4 x just fine. Can I integrate this part just fine? Not really. Okay. So I'm going to break this. So we know we can break apart and do each individual piece. Alright, let's do the easy ones first. What's the antiderivative of 1/4 x? And let's do this other easy one. So that would be minus 1x. Those are the nice ones. I just moved them around. What would I have to do to integrate these things? U's. What would my u be? Du? Dx. So it'd be 1/2 du is equal to x dx. Okay, so this one, if I go ahead and change my limits, you put in negative radical 15, you get 15 plus 1, so 16. Put in a 0, you get 1. 1/2 u to the negative 1/2 du. The other one would go from 0 to 16. 1/2 to the negative 1/2 du. You guys still with me? Okay. Let's go ahead and just finish these intervals here. What is the antiderivative of u to the negative 1/2? This would be a u to the 1/2. Whoops. This should be a 1, shouldn't it? Now we just have to put in all this stuff and evaluate. If we put in 0, I get 0. If I put in negative radical 15, I get 15 over 8. And then this, 15 over 8, let's see that. This would be the square root of 1, which is 1, minus the square root of 16, which is 4. It is possible to have curves that meet multiple places. And when this happened, was the same curve on top the entire time? No. Do you know, can anyone guess what the answer would have been if I just integrated from negative radical 15 to positive radical 15? It would have been 0. because you would have had to do one on top the whole time. And so one of these would have turned out to be negative and the other was positive, and they would have canceled out. So it is important to break apart each of those and to make sure you have the right curve on top each time. Now, let's say I integrate one and I didn't graph it to figure out which curve was on top, and I got -2 for my answer. What do you think the answer is supposed to be? +2. So do you have to go back and rework the entire problem? No, you just need to realize that its area, it should be positive. So technically you could set it up with either one on top, but then at the end you have to do the absolute value, okay? So that is another option, to just do the absolute value at the end. I think it's still easier to figure out which one's on top, but if you mess up, that means you don't have to redo the whole thing. You just have to go back and do the absolute value of that answer and recognize that the area is always positive. Okay, I am going to stop here for today. So, I'm going to go ahead and give you guys a couple to try on your own. They're nowhere near as nasty as that last problem I did, I promise. So, three problems.